Those of you who chose to come in person instead of watching on TV, welcome. It's nice to have you. Sense of solidarity, it's good. I know the homework's due tonight, and everybody's working hard, I'm sure, so good luck with that. And don't forget that you got to get the git incantations exactly right this time. So leave yourself time, at least an hour, I would say, to mess around with git and feel like, yeah, you understand how it's working and you're submitting right. Maybe peel off one of the team to go look at that before things get urgent. I'd hate to see people lose points because they didn't submit properly, right? But it's important, and I want to make sure you guys do it correctly and not burden the TAs with 27,000 exceptions. Okay, I realized at the end of last lecture, as we were peeling through the summary, that there was a really interesting little tidbit embedded in the conclusions that somehow didn't make it into the content of the lecture. And it's this last line of this second to last slide. We talked about B-trees and ISAMs and all that good stuff. And then, one of the things we spent a little bit of time on last time, but not a lot of time, was how this relates to the previous lecture's discussion of alternative 1, alternative 2, and alternative 3 indexes. So let's take a minute and review those. And then I want to just kind of hammer home this point in yellow. Okay? And you may see where this is going, but it's worth the review. So remember, an alternative 1 index, which could be a B tree, but it could be a hash index or something. But I'll draw it as if it's a B tree. The data, the actual data, is in the leaves of the tree, is in the index, okay? And in a B tree, that means the leaves of the tree. So in our B tree, right, there's going to be this tree, and then there's the bottom level of the B tree with a linked list of pointers, right? So this is the leaf level of the B plus tree. Remember, in a B plus tree, the true data is always in the leaves. And in an alternative B plus tree, these data items that are in the leaves are actual records in the database. These are the primary copies, the only copies of the actual full tuple. Okay, so if you're looking for students by GPA, you can look them up by GPA, but the actual student record is here in the leaf of this GPA B tree. All right, so this might be a B tree by GPA, but the full tuple is here in the leaf, and only here, okay? That's alternative 1. So if you have another index by, say, student ID, it would not be able to be alternative 1. It would be alternative 2, and it would have pointers into this B tree, all right, because that's where the tuples are. It would have record IDs, which are page number, slot number, that reference leaves of the B tree. Make sense? So that's alternative 1. Alternative 2, index contains key, comma, RID pairs. In a B tree, they would be in the leaf. So in the leaf of the B tree, in this picture, we might have a B tree on email address, okay, of a student. And then in the leaves of the B tree, we'll have the keys, that is to say the email addresses, and a record ID pointer to somewhere else in the database. Now in the pictures in the slides, the somewhere else was almost always a heap file, and I drew it as a big wide rectangle at the bottom of this B tree. There's an additional level, which is, say, a heap file here. Okay? But it doesn't have to be a heap file. It could be another index that's alternative 1, right? Okay. So these record IDs, they'll all go to the same place because the actual relation is only stored one place. That place could be a B tree. It could be a heap file. And then alternative 3 is a variant of alternative 2, which is key, comma, set of RIDs, which deals with duplicate keys a little bit more compactly, right? Okay, so that's the reminder. Having seen this, what I want to emphasize is this last bullet now. If your data entries are data records, which is to say alternative 1, so your B tree, and your data entries are data records, what happens when you split a leaf page? The tuples move around, which means that their page ID changes, which means that their record ID changes. because record ID is page ID, comma, slot number, right? So let's remind ourselves of that. RID is of the form page number, slot number, right? So if you split a B tree in alternative 1, things change page numbers, which means the record IDs change, which means all pointers into that alternative 1 B tree have to be updated upon the change, which is expensive. All right? If you have a lot of alternative 2 indexes pointing to an alternative 1 index, when you grow that alternative 1 index, you update all the other indexes to fix the record ID pointers. Right? And it's just a lot more IOs upon update. All right? And note also that the insertion you do into that alternative 1 tree affects not just one record, it affects many records, because when you split the page, many records change record ID. And those records, let's say they're all people with GPA 2.4, right? The emails for those people are not alphabetically co-located, right? So when we go to the email index to update all the pointers to the GPA 2.4 students, they're going to be bouncing around in this email index looking them up, right? And they're going to be in different places. So you're not going to get any cache locality in the email index when you update the GPA index and split a page. So it is kind of costly. It could be many, many random IOs if you change a record ID in a B tree. So it's a design decision that can bite you at update cost, even though it might give you more efficiency if you search into that index very often, right? The benefit of alternative 1 is you don't have to follow yet another pointer once you get to the bottom of the index. But the cost is on splits. You have to do more updates to other indexes. Got it? So all that was, hiding in the last bullet of a summary slide. I apologize. Okay. The rest of the summary slide is summary. So key compression, we learned last time, will increase our fan out, which could decrease the height of the tree, which is a big win. We learned about bulk loading. It's much faster than multiple inserts. And then to emphasize one more time, B+ trees are widely used because of their versatility. They handle range queries as well as point lookups. And it's worth saying that they really are the workhorse of the bottom of the database if you have the kind of system that does a lot of small lookups. Okay, the workloads that happens for are typically what are often called transactional workloads. Like people go to a website and they do a search for a specific, say, product name, or they do a purchase and you have to record their purchase. Those are small lookups. This is very different from what are called analytic workloads, where like you look at the log of all purchases people have done because you want to build a recommender system and you want to know what people gather what things. So if you're doing a big aggregation query, select star from table, group by this, then you look at all the tuples, you'll use sequential scans typically. But if you have a workload that's mostly like, update the amount of widgets we have in the inventory with number 472, like a purchasing system, you'll typically use B trees or something like them quite heavily. So in these transactional systems, B trees are a real workhorse of the system, so they get tuned a lot. And in modern days, what that means is that you may find a lot of hackery in the system on the main memory representation of a page, so that, say, binary search on the page goes really fast. You may find a lot of hackery that we'll learn about later in the semester in some detail about how to do concurrency control on the B tree, making sure that multiple people can be wandering in there, some of them doing insertions and deletions, while others are doing searches, right? So there's a lot of optimization that'll go into your index B tree package, and with flash technology and with a lot of things being in memory and then worrying about cache locality on the processor, you'll find in the field that these things get to be pretty tightly tuned, and we won't get time to cover a lot of these tricks in class. One more comment along those lines is that for systems that are geared towards main memory databases, where the data really should never go to the disk except for failure recovery, there are a bunch of systems now where that's totally feasible because all your data could fit in RAM. B+ trees get changed around typically in those implementations, and they don't look exactly the way we learned them here because some of those overheads about disk accesses make less sense when you've got an in-memory data structure. So keep in mind that the database field and the software artifacts people are building, a piece of it is shifting to in-memory implementations. And some of the things we learn in textbooks about databases and disk blocks may still make sense in memory and may not. And so we won't probably, maybe at the end of the semester, we'll get to do one lecture on like something fun with modern main memory databases from the last like 2-3 years. Probably we won't, and I'll just flag this for you. So when you go out in the field and you talk to people, you'll be aware that your textbook database class is being revisited as we're looking at in-memory databases, okay? There's been actually some cool work on this at Microsoft, actually. So Microsoft Research did a lot of interesting work on this that's being rolled into their product, into SQL Server. And some of that is production now, and some impressive things. So I can, if people are curious, post to Piazza that you'd like to see links to research papers, and I can point you to some of that stuff. Okay? If I don't hear from you, I probably will forget. All right. So much for B-trees. So we're going to shift topic fairly significantly now and shift sort of flavor. One of the cool things about database as a field, as a technical field, is it's kind of a microcosm of a lot of computer science. Because really, if you say, well, I'm the part of computer science that worries about data, you have to do all the computer science. You know, because like data is everything at some level. And so these systems are microcosms of a technical community that's had to think pretty full stack about a lot of issues in computing. And that means that this class tends to have a lot of different topics that have pretty different feels around them. So what we're shifting to now is a conversation about languages. Right? We're shifting away from a conversation about performance and implementation. We're going to shift to a conversation about domain-specific languages and semantics. Okay, so it's going to have a very different flavor. You may like this better, you may like it worse, but it's just different. All right? To give some context, in the context of our system stack, you know, we were down a level into files and access methods, and we'd been working our way up, right? And we started with relational operators like joins and things like that. And so we've filled in, to some degree, an implementation of the whole bottom of the system below the query optimizer. We've covered everything. Okay, so that's kind of cool. Like right now, you could build a single-site database where you have to program it in iterators, which is sort of like it's sort of like MapReduce, really. You've sort of learned the crux of that, how to build a iterator-based data flow system, right, with joins and aggregations and all that. What we're going to do now is present a formal language for those relational operators, things like join and group by and things like that we've learned how to implement. We'll now introduce a language to talk about it. Okay, and you might ask, why would I want to do that? Okay, we'll talk about that a little bit too. So relational query languages were the topic of much study in the 70s, I would say, and sort of got baked back then, although people keep wanting to revisit them in the context of XML or JSON or whatever's the next file format that comes along. But the guts of it end up looking a lot like relational languages with some extra secret sauce. Okay, so this is the foundations of the various languages that keep getting invented and reinvented. So like if you learn the MongoDB query language, knowing this stuff will help you understand that very quickly. It's not like it really changed that much when we moved into JSON objects. All right, but query languages, what the heck are they? They're domain-specific languages for dealing with data, for manipulating and retrieving data from databases. Okay? And after all, there is really nothing else to do in computers but manipulate and retrieve data at some level. You can disagree with me, and we'll see. But like, you probably don't want to go back and do your 61B homeworks in SQL. That'd be kind of weird. But we actually will make you do a little of that in your homework for this class. All right? Because it's actually quite doable. And the thing about implementing it in Java is, okay, parallelize that, man. You're like, I don't know how to parallelize my 61B implementation of I don't know, some data structure, quicksort or something. It's like, that's right, because you wrote it in a sequential language. If you wrote it in a relational language, it would parallelize sort of automatically. Right? And so there is issues of scale that make these languages interesting for things that aren't like employees and departments and students and boats and reservations. Okay, so we'll get to that a little bit. But query languages are very expressive, actually, some of them. Relational query languages come from a foundation in first-order logic. So the guy who invented this stuff was a cranky British mathematician named Ted Codd, and he sort of came into this field where IBM had all these products with ISAMs and stuff, and he's like, this is all just set theory. It was ridiculous. Let me just write it down. And so he invented these little languages that were just based in formal logic, and they're very simple. And I think by our standards today, it's like obvious undergraduate material. But in 1969, people were like, no one could understand that. It's got like upside-down A's in it and backwards E's and things. That's fine. All right. It's like generational, right? At the time, it was perceived as being very mathematical. I think today, it's pretty straightforward. Anyway, so strong formal foundation. There's power in that formality, though, as we'll see. So they're simple languages. They're crafted just to do enough for queries, and that's an interesting debate over time, how much is enough in one of these languages. So we won't get to talk about enough in this class, probably. But they're designed to be simple, small, domain-specific languages for data that are powerful in the things they can do for data, all right? The other thing about having formal semantics is they're going to allow us to do a lot of optimization of your queries. And that will come up over and over in the course of the class. We'll be spending a fair bit of time on how we translate from these language statements to execution strategies via optimization. So I threw this slide in last night because I was feeling sheepish about shifting you from B-trees to relational algebra. Why bother with this formalism? After all, we already have physical data flow. I taught you about iterators. You learned MapReduce in 61B, which is, just the way of applying opaque lambdas, right? I don't know what's in your functions, but I know I can map them or reduce them. So why do we need anything more than that? And at some level, maybe you don't. Right? And in fact, about 3 or 4 years ago, if we had a conversation about MapReduce in Hadoop in this very room, because it was being taught at Berkeley, or in the industry, people would say, you don't need anything more than MapReduce. MapReduce lets me do everything I want. Look, here's word count. Here's a machine learning algorithm. I've implemented 7 things in MapReduce. It's fine. But actually, even in the 3 years that have passed, most of the industry is saying, boy, finding programmers to write things in MapReduce is really expensive, and you know what? They're really slow when they do it. They write all this Java, and then we have to debug it. Can't we just get SQL back, please? And so there's a lot of companies and open source projects that just put SQL on top of MapReduce, which is what Spark SQL, which you've been hacking this week, is. Okay? So in fact, yeah, you often do not want to program at that physical level. It's just too detail-oriented for a lot of very straightforward tasks that are well suited by a relational language. Okay? So the other thing, though, besides convenience, that's really important is this notion of semantic transparency. If you write a map function and give me f, right? You say map, and here's f, the function I want you to run. I don't know what f is. I'm not supposed to know what f is, right? It's opaque. That's fine, and there's a certain cleanliness to that separation of concerns, but it makes it very hard for me, the system executing your code, to optimize anything, because I don't know what f does. What we get in a language that's more suited to the domain and more semantically rich is we can understand the details of what these expressions are doing, and then we can play games under the covers to make them go faster. Okay, so having this transparency of what is the user trying to say and not making it opaque, but making it very clear in the language allows us, especially when you have a little language, like a relational language like relational algebra, to do pretty rich program analysis, and that program analysis will help us with query optimization for sure. Okay. We're getting the user to specify their intent in a way that the system can understand. All right, but there are other topics that analysis actually helps with that we won't cover in this class that are really super useful in practice, and that the functional programming and MapReduce community is kind of sneaking up on all over again. Things like data lineage. If you get an answer, where did it come from? Why do you have it? So there's an answer to one of your queries. Where did it come from? Well, if the query was written down with a whole bunch of black box code in Java, that's a really hard question to answer. Why did I get a 17 in my answer? I don't know. We invoked your code, man. It gave me a 17. What more do you want from me? If you say it in a relational language, we might be able to say, the following tuples from the database were put together through joins and selections and projections and aggregation to produce that answer. Maybe you want to go look at those tuples. Or maybe you want to look at the operators along the way that put those tuples together. So we can get pretty rich data lineage by inverting these queries because we understand their semantics. Similarly, things that we won't be able to talk about yet, but we could talk about later in the semester around being able to store the outputs of queries. So a view is just a query. A materialized view is a query whose output you have saved, so that later on, if you ask the same query, we've already got it answered. Well, what do you do with that thing when, say, someone updates the database? Now the output of the query should change. I want to change that stored output without rerunning the query from scratch. How do I do that? So again, if we understand the query in detail, we can often find a delta query to run that just makes a little bit of work to change the output based on the change to the input. Can't do that if it's expressed in a black box function f. Right? Updatable views. I have the output of a query. I want to change the output of the query, and then I want you to figure out how to change the database to reflect that the output of this query changed. So how would you make it that the answer to this query is different? I'll give you an example of that. I did a bunch of stuff with my database. They were stock transactions, right? And I lost a bunch of money. I would like to say, make me money on the answer to that thing and have you figure out how to change history so that you would have chosen better stocks, or your stocks would have had better prices or something. You want to go back to the source data and change the source data to get the outcome you wanted. Right? It's a little bit of a silly example because, of course, it's the real world and you can't go back in time. But you sort of get the point. So anyway, these are topics we won't cover in detail, but having a rich formal language enables a host of goodness. Okay? So even though this could be potentially tedious, honestly, for the next half an hour, a lot of good comes out of having a formalism. Right? And some people love formalism. So maybe you will find it not tedious, but lovely. Okay. Just to be very clear, the standard viewpoint is that query languages are not full-service programming languages. They're little languages. They're domain-specific languages just for data processing. And we don't want a Turing-complete language exactly because that would be too hard to analyze. I want a little language that we can do good analysis on that's just enough for what I need. So typically, they're not Turing-complete, or at least not without calling out to some other language. Like you can invoke Python from Postgres as SQL, but that's outside the language, sort of just a call out, right? And they're not intended typically, they're viewed, database languages were traditionally viewed, they're not calculation languages. They're not general purpose computing languages in the sense of I would like to compute some things. They're languages for data, right? So that's the traditional viewpoint. But the funny thing, for the reasons I was intimating earlier, is that in recent years, anything you want to compute of interest involves a large data set, right? Almost all of you will have a job in an environment where there'll be a big data set in the background somewhere that's driving that thing. Even if you're in mobile, right? Building mobile apps, the thing in the cloud's got lots of data. It's pretty interesting. So it's like everything interesting in computing involves lots of data and lots of machines. And actually, query languages with extensions are quite powerful for expressing algorithms at scale in the way I described. Like parallelizing Java code, very hard. Parallelizing SQL, quite easy. In fact, we already saw how to, really briefly, and we'll go back to it, but we talked about how easy it would be to parallelize hash join or partition, or the sorting algorithm we learned, right? And that stuff it's really almost that easy. There's scheduling problems, et cetera, but it's fundamentally kind of easy. So things like query languages, like MapReduce, which is data flow underneath the query language, these are all very valuable when you're trying to scale up. And so query languages are kind of having a renaissance as maybe this is a good framework for programming many things, okay? In fact, and this has been a focus of work in my group, they could even be an attractive choice for thinking about not even large-scale analytics jobs like MapReduce, but little asynchronous programming environments like programming user interfaces, which are kind of event-driven, right? Or programming little protocols and networks. Actually, you can think about those as streams of data going through little joins and stuff, and some of these problems turn out to be really pretty and easy. So we have a language called Bloom, which I encourage you to look at for doing distributed systems in a query languagey kind of style. A much more sort of applied language that's used in industry quite a lot is RX, which came out of Microsoft originally. So like your Netflix browser is implemented in RX. What else is, there's stuff at Facebook and Google, I think, that's implemented in RX as well. It's become pretty popular. Microsoft open sourced it, and the guru of RX left Microsoft and is kind of running around showing it to people. So RX is a language of sort of data composition. It looks a lot like relational algebra for streams. Right? It's used for GUI programming largely right now. So there's a fun article you can dig up actually in the CACM, which is the main magazine of computer science. It's called My Mouse is a Database. It's by the RX guy, and it talks about how he converts streams of inputs to the screen into essentially things you want to query. And that's how you program UIs. So you're going to learn about good old-fashioned query languages, but be aware that this may become a bigger part of your future than just databases. All right. There's two classical languages that Ted Codd invented in the late 60s, early 70s. One is the relational algebra, and the other is the relational calculus. And they're different in a way. So the relational algebra is kind of an operational language. It tells you how to do a sequence of events, very much like iterators and data flow that we've seen. All right, so it's useful for representing kind of execution plans, but representing their semantics, not their detailed implementations. All right, the relational calculus is a purely declarative language. It's a logic language. It actually has for alls and there exists and good stuff like that. So it looks a lot like first order logic. And it says nothing about what order to do things in. So you describe only what you want. You do not say anything about how to compute it. Right, so that's what we mean by a declarative language. Right? And the syntax of the relational calculus describes the output of the query. That's exactly what its meaning is, which is kind of interesting. It doesn't describe a computation. It describes an output. Okay. And the relational calculus is essentially what SQL is. SQL is roughly a declarative language along the lines of the relational calculus by way of many English words and some mixed metaphors. So, but it is kind of the foundation for relational calculus. And Ted Codd won the Turing Award back in the 70s for essentially proposing that the relational model was good for databases, defining these two languages, and proving that their expressivity is equivalent. Let me say that again. Their expressivity is equivalent. Anything you can say in the relational algebra, it's not Turing complete, so you can't say everything, but anything you can say in the relational algebra, you can say in the relational calculus, and vice versa. Seems like a pretty academic exercise. But the thing that it gives us is it allows us to take SQL queries, which just say what the output should be and don't say how to do it, and compile them into relational algebra queries, which are pretty close to query plans. So the foundation of how a database system is built, where you start with a declarative expression in SQL, you compile it into iterators, comes from this theorem, essentially, that they're equivalent. So in a classical relational database class, I would teach you both these languages, and we would at least make an argument, maybe a proof that they're the same. I'm not going to teach you the calculus, because it's really not very useful. You won't pick it up again by nature, ever. So I won't teach you the calculus. I am going to teach you the algebra, because it's a sort of cleaner way to think about query plans. And of course, you'll learn SQL, which will be a stand-in. It'll be the declarative language we will learn is SQL. All right. So today's the algebra, though. Today we're going to learn the algebra. So some preliminaries. What's a query? Well, the inputs to a query are relation instances. Remember this terminology. There's a relation, which is a description of a table. It's the schema and the instance. The instance is the contents. Okay. So the input to a query is an instance. It's a database table with actual data in it, particular state of the database. Okay. The result of a query is also a relation instance, right? So it's a closed language. It takes in relation instances and it puts out relation instances. And that allows us to compose the operators of the language one on top of the other. Right. So the schemas of the input relations are fixed. So your query is going to have certain input relations and they'll have fixed schemas. The schemas of the outputs are also well-defined and fixed. So it's a strongly typed language in that sense. You give it input tables with schemas. There's a well-defined output table schema as well. And you can figure out the output table schema from the query language syntax. And we'll see this. All right? This is just the very first place where we have a contrast with what you're used to in MapReduce. In MapReduce, right, you get keys and values in and you get keys and values out, but there's no way to know like what kinds of keys you might ever see, what are the types of the values. All that kind of stuff is left up to the programmer. It's very free, which is nice, but it makes it very hard to analyze. Here we'll know exactly what the types of the inputs and outputs are. Now, the pure relational algebra, which is what we'll talk about today, has set semantics, which is to say, in a relation, there are no two rows that are exactly the same. All right? If you try to put a second copy of a tuple into a table, it's like it doesn't matter because you already have it, is one way to think of it. But there's no duplicates in these tables. By contrast, SQL has a multi-set semantics, which is like marginally more confusing to think about, and we'll just not do that for today. Okay, so today we'll stick with the classical relational algebra. When we do SQL, we'll have to worry about duplicates and maintaining the right numbers of duplicates through operations. Today we don't have to worry about duplicates. Sometimes actually it's going to cost us to have to get rid of duplicates, which is going to be a drag. All right, there's only 5 methods, operators, whatever you want to call them, in the relational algebra. Selection, projection, cross product, set difference, and union. Each operation returns a relation, so you can compose these together. You can string together sentences, functional expressions of these operators. All right? Really briefly, and we'll go through them in detail, but selection selects a subset of rows. It kind of allows you to make horizontal decisions about rows in the table. Projection retains only desired columns, so it's choosing which vertical columns you want. Cross product's going to let us combine 2 relations and concatenate their results. And then set difference and union are your familiar set operations, but over relations rather than over set items. Okay, and let's go through them in detail. In this lecture, as in the book, we will have the very exciting boats database. Okay, so the boating club has boats, which is a table that has BID, BName, and color. It has a reservations table with an instance R1. All right, so R1 is the state of the database today. There's 2 records in it. And that's the reservations table, essentially. And then we'll have 2 different instances in our examples, just so we can see some variety, of the S relation, which is the sailors relation. All right? So S1 has 3 tuples. S2 has 4 tuples. It's missing Dustin, and it added Yuppie and Guppy. Okay? So this will give us a little variety to play with as we go. All right. First operator, projection, pi. The way you write it is pi subscript, list of column names you want to keep. So in this case, pi sub age of a relation S2 says, please produce a table in the output that has the column age from the input. But you could have more than one column. You could say pi sub S name comma rating. All right? And it just basically retains only the attributes of the input that you want that are in that list. So the schema of the result is apparent from the syntax, right? It's the column names that are in that list with the same data types as the input columns of those names. Yeah? So it's very straightforward. We know exactly what the types are and the names, actually, of the output columns based on the input columns. All right, the projection operator, however, because we said we're not going to have duplicates, if you implement this, you have to actually eliminate duplicates. Because when you do projection, you introduce duplicates. We'll see this in the next slide. Now, in practice, real systems don't do duplicate elimination unless you ask them to. Why would that be? Suppose, well, let's come back to that question in a second. OK, let's look at an example. We're going to do projection on the upper right of sname rating on S2. So here's S2 on the left, SID, sname, rating, age. Here's the projection on the upper right of sname, rating. All right, you'll see we only get those two columns, sname and rating. Here's the projection to age. Not only do we only have one column, now we only have two rows because we removed the duplicates. All right, so the output may be fewer rows than the input because of duplicate elimination. OK, suppose I gave you a table with 1,000,000 rows, and it had a column called gender. What would be the projection? What would be the size of the relation projected to gender? Maybe 2 or something, depending on kind of the way you view the world, but it would be a small number, all right? Certainly wouldn't be 1,000,000 unless we're really in an advanced age. And so I guess what I'm trying to say is that you're going to do a big change from the input to the output. What is, why might you not do that if you're building a system by default? Why might you not do that? Is this the question from the previous slide? Yeah. Awesome. So if you know this, if you don't eliminate duplicates, then the number of rows in the output is equal to the number of rows in the input. And that might be useful for a bunch of planning purposes. Maybe you need to figure out how much memory is going to be used by the next operator, which might be a sort. And we need to know if it's square root of b big or bigger. Or actually, it's b squared big or bigger, right? So we can do 2-pass sort. So we'd like to know how big the output would be next time. And we know for sure, if we don't eliminate duplicates, it's the same size as the input. That's a great point. What might be another reason we might not eliminate duplicates by default? Well, how would we eliminate duplicates? What algorithm might we use? Sorting. We might use sorting, or we might use hashing, right? Both of which are expensive, right? If a big table, you have to sort it or hash it, it's going to cost you 2 passes of the table, at least. Okay? So it's expensive. So you don't want to eliminate duplicates if the user doesn't care. Okay, so by default in most systems, you wouldn't implement duplicate elimination unless they ask. But in the pure relational algebra, you have to implement it, okay, to get the right answer. All right, fair enough. I just want you to sort of focus in on that. It's going to affect the sizes of the outputs of our table. So projection, we know the widths of the table. We know the types. We know the names. But we don't know the height of the table. It's smaller than the input, but we don't know how much smaller. Okay? So that's projection. Selection selects rows that satisfy some selection condition, which is a Boolean expression, okay? True-false expression. And the result is a relation with the same schema, because we're just picking rows out. Those rows will look just the same at the output as they do in the input. So the schema of the output is the same as the schema of the input. Do we need to do duplicate elimination for selection in order to maintain our no duplicates rule? Anybody? How many people think that we need to do duplicate elimination after selection? Please raise your hand. How many people think we do not have to do duplicate elimination after selection? Please raise your hand. Maybe it's an obvious point. OK, fair enough. We're, in essence, throwing things away, right? We're not going to select all of it, but the most we can select is everything. And everything didn't have duplicates. So something less than everything certainly doesn't have duplicates, right? So selection can't generate duplicates. Here's an example. Rating greater than 8. All right? It's going to not choose that row. And it's going to not choose that row, and it's going to choose all the other rows. What remains from the selection is clearly a subset of what we had. What we had no duplicates, so this has no duplicates. OK. Here's a query that takes that selection, rating greater than 8, and projects it to sname, rating. Right? So it's going to throw out those columns, leaving us with those two things. Right? And so you can see how a combination of selection and projection can let us zoom in on certain cells, so to speak, of the table, right? And put them together. The ability to cross out rows, the ability to cross out columns. All right, union and set difference are these set operators, but they're on relations now, not on sets. And so in order to make sure they make sense, those relations have to have the same schema, more or less. Right? right? You can't take the union of something with 12 fields and another thing with 3 fields. It's like you'll end up with a relation that's kind of got ragged-sized tuples, and it won't be relational anymore. It'll be, oh my God, XML. So we're not going to do that. Okay, not yet. We can do it in XML if you want, but it gets ugly. So we're going to say that 2 input relations have to be union compatible, which means that they have the same number of fields, and the corresponding positions, position 1 of this table, position 1 of that table, have the same data type. Or maybe a union compatible data type. So when you get into details in an implementation, you might say, fine, we can union integers with floats, and we'll promote the integers to floats. Okay? So you can play some games like that. But you can, just for simplicity, let's say that the types have to be the same. We don't have to have the same column names. All right, that's the one thing we'll be lenient about. All right, so pretty straightforward. The union of S1 and S2 here is that. Note that S1 has 3 rows, S2 has 4 rows, and S1 union S2 has 5 rows because of duplicate elimination. So we do have to do duplicate elimination after union, right? Okay. Set difference, as you would expect, is going to remove the things from the right-hand side that are in the left-hand side, all right? So S1 minus S2, all the things in S1 that are not in S2. S1 is smaller than S2, which is a little, that's okay, right? There's nothing wrong with that. We're going to take away from S1 those things that are in S2. So the output is going to be a subset of the left-hand side, which is S1, right? Make sense? Right, so it's perfectly possible to have the cardinality of the right-hand side of set difference be a bigger and a superset of the left-hand side. That's fine. Yes? Right, so the question was, is there some notion of like, if something's in the right-hand side, is it somehow, do you get it like a negative somehow from the left-hand side? No, because we're not doing counting. Right, so all things can be present or absent. And if something's present in both S1 and S2, then it's absent in the output. If something's present in only S1, then it's in the output. If it's present only in S2, it's not negative, it's just not in the output. Okay? However, when you do multi-set union like in SQL, then you start to do counting. There's 3 of them here, and there's 2 of them here, so the output will have 1, stuff like that. You still don't go negative. All right, so we tend not to represent negative information in these things. But good question. So for now, though, we don't have to worry about counting. It's just either there or it's not, and to be in the output, it has to be on the left-hand side. Here's S2 minus S1, all right? Not a lot of symmetry there. That's okay. You know, they're different. Set difference is a funny beast, actually. So it turns out, like, this is all obvious, right? Blah, 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 set difference, set union. We knew this. You learned this, like, maybe freshman year, maybe when you were in elementary school. Set difference is funny. So almost all the relational algebra, in fact, all the relational algebra operators except set difference, are what's called monotonic. What that means is that as the inputs grow, the outputs grow. Another way to say that is, if you take a query like over some tables, so Q over some tables R1, S1, T1 that are instances, and then you take one of those and you replace it with a bigger instance, R2, that has some extra tuples in it, the output will be strictly a superset of the output on the smaller input. So as we inserted things into R, the result of Q got bigger, set-wise. Right, that's the monotonicity property of these operators. And that's true for everything except set difference. In set difference, if we put more stuff in R1, S1 minus R1, if we put more stuff in the right-hand side, new tuples, they will knock out some of the tuples on the left-hand side. So if you grow R and you choose R2 that's a superset of R1, then S1 minus R2 is actually potentially a subset of what it used to be. Because by adding things that we subtract away, the result may have fewer things, right? So this turns out to have all kinds of interesting implications. A simple one of this is when you implement set difference, it's a blocking operator, by which I mean you can't compute the answer to the query till you've seen all the tuples of R. So you have to say get next on R, S minus R, right? Say get next on R until you've consumed all of R, and only then can you start producing tuples of S. Because think about it. If you have a tuple of S, you're like, haha, I have a red pen. If there's no red pens in R, I can output a red pen. When do you know there's no red pens in R? Only when you've seen all of R. Okay? Well, that could be kind of a drag if you don't really know how big R is. Right? So what do you do on this side of the operator? Well, you kind of have to wait until you do all the computing on this side of the operator. All right, so you have to do what's called a blocking operator. There's no flow upstream till all of R has been read. That's kind of a drag, all right? It gets to be a much bigger drag when we start using these kinds of operations for broader classes of computing, like distributed systems or interactive interfaces, where suddenly the world kind of stops while you're waiting for something to come. And that something that's going to come isn't a scan of a table. It's like you're waiting for a network message and you don't know when you're going to get it. So if the R's were streaming in off the internet from agents, we'd have to wait for them all to send all their stuff, and that might take an arbitrary amount of time, and we'd just have to wait, which stinks. And it turns out this whole notion of non-monotonicity is really important, and I won't go on much more about it right now, but set difference is the only operation that has it. And that non-monotonicity baked into set difference, anytime you see anything in your queries that feels like blocking or it feels like removing things, you're going to use set difference to say it. Right? It is our one non-monotonic operation. Okay. Cross product. We've already I drew this first week of class, I think, but right, it's the Cartesian product of the space of tuples in S and tuples in R, all pairs of S1 and R1. How many rows are there in the result, Q? R1 cross S1? The number of rows in R1 times the number of rows in S1, right? Okay, so we know the size of the output, and we know the result schema. The result schema is one field of S1. It's all the fields of S1 concatenated then with all the fields of R1, if it's S cross R, okay? So you take all the columns of S1 and you just concatenate out the columns of R1. And the field names are going to be inherited when possible, and we'll see what happens when they're not possible. So if you have a naming conflict, suppose you're joining two tables and they both use the same column name, then you're going to have to do something to rename the columns of the output. So there's this little annoying little extra operator for syntax called the renaming operator row, where you can take an input, like the input here is here, it's the second argument, and in this case it's an expression, S1 cross R1. And the renaming expression, which is the left of this comma, gives an output name for the relation output and a mapping of column positions to column names that you want to change. So this is saying column 1, call it SID1, column 5, call it SID2. Okay, so you can always make sure to impose names when you have ambiguity, right? So here's a cross product of R1 and S1. We concatenate the schemas, and we form all pairs of rows. And you can see that because they both have SID, we don't actually have names for the column 1 and column 2, 3, 4, 5. So we'll have to use a renaming operator to rename. Okay. Now, intersect we would have expected to see, but we don't need intersect in the language. Intersect is just a composition of operators we've already seen. Okay, but it's handy. So let's define intersect with respect to the other operators. So there are a bunch of operators we like they're essentially macros on the basic 5. They add no computational power to the language. They're just shorthand macros. You can express them with the basic ops. Intersection, you know what it is, right? It takes two input relations, which must be union compatible, otherwise it wouldn't make sense. And it returns those things that are in both relations, right? So what is R intersect S? How do we express that in terms of the operators we've seen so far? Let me give you a head start. Maybe we can make it R minus something, because after all, it's going to be a subset of R, right? Anybody see what it is? It's R. What do we take away from R? It's all the things in R except those things that are not in S. Right? It's all the things in R except the things in R that are not in S. Okay? Right? So it's this. Yeah. Cute. All right. That's what it is. So intersection of two relations, pretty straightforward. Same schema. The tuples that are in both, right? All right. Now join is also a compound operator. It's not part of the relational algebra technically. All right. It's cross product followed by selection. And for some variations of join, we might also make it have a projection for what's called the natural join. What's the natural join? We're just going to write the natural join as R bow tie S. R bow tie S, which is the natural join, is defined as, well, here's a way to think about implementing it. This is not a definition. This is operational, but it's fine. Compute R cross S. Select the rows where the attributes appearing in both relations have equal values. So they have to actually match on attribute name, like SID from this table and SID from this table. So if you have two columns here that have names that both of them appear here, then you're joining on pairs of like SID comma last name, SID comma last name. All right, so you find all the matching column names, and then you look for matching values in the columns with matching column names. I'll show you this in a minute. So So you select rows where the attributes that are in both relations have equal values. It's kind of an implicit equijoin on all of the matching column names. And then we're going to not keep because we're matching like SID here equals SID there, there's no point having two SID columns in the output. They're going to have the same value. So we can drop one of them. So we're going to project onto only unique attributes with one copy of the common attributes. All right. This is a stupid algorithm because you form the full cross product before you do the selection. We'd much prefer to do hash join, right? This is an equality join. So we should do hash join or sort merge join or index nested loops join or something. This is just a sketch. So here's the natural join of R1 and S1. So it joins essentially the SID equals SID. Right? That's what the natural join is here. The matching column names are SID. So we'll look for matching SIDs. And what are we going to get? We're going to get 22 and the first thing is Dustin, and 58 and the first thing is Rusty. So we should get 2 rows in the output. And notice only one copy of the SID column because we projected it down to just one of them. Okay? That's natural join. The other types of join, theta join, instead of having this weird matching name equality, you can put any predicate you want there. Any conjunction, or even you can do disjunctions and negations if you want. Any Boolean expression over the columns that evaluates to true or false can be your theta. All right, and we're just going to compare up those columns between R and S based on that conjunction and produce the output. So here's an example. It's actually the same query as last time, joining on SID, but we've made it explicit as an explicit theta subscript of the join bow tie. And there's the output. Note that this one doesn't do any automatic projections. You have to ask for them. So theta join, no free projections involved. The result schema is the same as the cross product, although, of course, because of the theta, there may be fewer rows in the output than in the cross product. We'll often talk about equijoins, which are theta joins where there's only equality predicates in conjunction with each other. So, column 1 equals column 2, and column 3 equals column 3, et cetera, et cetera. So T1, T2, T1, T2. Why do I only want to allow ands in my equijoins? Why not ors? Well, this is a little bit fussy, but if we only have conjunctions, then we can do things like use indexes with composite keys, or we can have a hash function on the concatenation of this and this, concatenate those together and hash them, and then this and this, concatenate those together and hash them and use a hash join. When you're doing conjunction, it's pretty much like doing a single equality. It's just that equality has little pieces to it. When you do OR, it's actually an if statement. It's like, if you match on this, you go to the output, or if you match on that, you go to the output. And that's really a union query, in essence. It's like a join, union, another join, and it doesn't fit into one join algorithm. You have to do the join kind of twice-ish. Okay? So we're only going to call things an equijoin if they're a single equality predicate or a conjunction of equality predicates. Example of an equijoin. Oh, no, more examples. Sorry. So now let's put together some queries. And so these should be examples of the whole language, I guess. Find the names of sailors who've reserved boat 103. Actually, let's take a stretch, because, as I said, this could be a little tedious. And then we'll go through some examples. All right. So I want to go through a bunch of examples of turning English language queries into relational algebra queries. It's going to exercise our understanding of the concepts. And I got to be honest with you, this is an easy thing to put on a test. all right? Because it's an easy way for us to tell if you're understanding stuff because you can just read off whether you got it right, right? Unfortunately, unlike other programming languages, you can't play with this one in an interpreter because I don't have an interpreter for relational algebra to give you. And so you just kind of have to make sure you understand it. It's not a very easy thing to try. There's no like tryrelationalalgebra.com that you can go and test it out in your web browser. So I apologize for that, but you should feel responsible for being able to string together these operators. If we forced you to program iterators like MapReduce style, and we gave you a join reducer, let's say, and we gave you a selection and a projection and all these things, we could give you programming assignments, but that seems like a lot of work. But that's essentially what we're doing. We're forcing you to program by stringing together these things. I'll make one more point, just to make this painfully clear. When we write something like R1 equijoin S1, and then let's project down to, I don't know, R1, SID, and select name, and then do a selection with like, SID equals 4. So that's a relational algebra query. You could write this as an expression tree, right? This is what a parser would do. It would kind of look like this. R1, S1, project, select, right? Hey, guess what? That looks a lot like a query plan, doesn't it? Okay. So these are pretty close to the query plans with iterators that we had before. They really, really are. Okay. It's just a functional notation or nested notation for trees. And the only thing that's kind of missing from the relational algebra are things like sort or unique, were some of the iterators we looked at that have no meaning to the output of the query in a set-oriented sense. So sort doesn't change the definition of the set at the output, because sets don't have a notion of being sorted. Unique doesn't change the definition of a set, because sets don't have duplicates, right? So we learned some operators and iterators that are important for implementation, but not important for the meaning of the query, and they're not in the relational algebra. But many of the things that we learned are in the relational algebra, and we're essentially composing data flow plans. So if you want, you can think about this as like MapReduce or Spark programming, okay? If you prefer, you can think of it as just a formal language. Anyway, you will be responsible to be able to do it. All right, find names of sailors who have reserved boat number 103. All right, we know the schemas of our tables. Here's one solution. Find the reservations for boat 103 from the reserves table. So select BID equals 103 from reserves. For those reservations, join it with the sailors. Now we've got the sailor names that are associated with those reservations, and then project to the sailor names. Now note that we needed both tables because the reservations had the boat ID, and the sailors had the name of the boat of the sailor, right? So the query asked about things that were in the reservations table and things that were in the sailors table. We had to form the join, even though the output only has fields from the sailors table, right? Okay, so sometimes you have to go through joins and stuff even though your output won't reference the tables you joined to. Here's a different solution, same query. In this one, first we join up all the reservations and sailors. So we get a list of all the boat IDs and sailor names and everything that ever were associated through reservations. And then we just pick out from that complete set the boat ID equals 103. And then we project down a sailor name. Right? It does give the same answer, and you should convince yourself that it does. Right? Which one do you think would run faster based on what you know about join algorithms? The first one. Why? Got it. In the first one, the selection on reservations is going to make the input to the join smaller, right? Fewer reservation tuples go into the join. We know joins are expensive, roughly, some multiple of the sizes of their inputs in terms of pages. And so making inputs to join smaller seems like a good idea. There's a big assumption in that statement, though. Anybody catch the assumption there? Well, the assumption is that selection is cheap. What if selection was wildly more expensive than join? Then it'd be a bad idea to do it the first way. Do you want to do it the second way? Okay. So most of the time in SQL, selection is really cheap. You look at a tuple. It's a map function, first of all, to be very clear, right? You look at a tuple, you can decide just looking at that whether the selection applies or not. So that's good. You don't need a whole lot of memory. You don't need to buffer anything. It just flows through. You can do your selections and only pass along the things that pass. So that's good. And in SQL, these expressions in the subscript of the selection are typically simple arithmetic operations. All right. However, when we're programming in like toolkit environments like Spark or modern databases with user-defined functions, Postgres is an example where you can plug user code into your selections. You could have, select from reserves where f, and f is a Python function. Okay. Maybe that Python function like goes and does lookups into Google Maps API. Perfectly reasonable thing to do. I want to find all people whose address is within 20 miles of a McDonald's, but all that mapping stuff is not in the database. It's going to make API calls out to some remote site. That could be super duper slow. And then selection becomes way more expensive than join. So it is possible that your selections will be expensive. In this class, we'll pretend it's the 90s, all right? I actually did my thesis on this topic. That was in the 90s. But we'll pretend it's the 90s, and I'm the only person thinking about this. And we'll assume that selections are cheap. Okay? Selections are free, essentially. As the data flows through memory, you do a very simple piece of arithmetic, and you just pass it along. No IOs. It's free. Joins are expensive. So we want to do selections before joins. Good. That all make sense, that little rant? Okay. Find the names of sailors who reserved a red boat. The information about the boat color is only available in the boats table. But we need to know about reservations, because I want sailors who've reserved the red boats. And I need the names of the sailors, which is in the sailors table. So I'm going to need sailors and reserves and boats. And I'm going to need to join them all together now. All right, well, let's do that. We need just the red boats. So we could push that selection in early. And we'll join that with the reservations to find all reservations for the red boats. And then we'll join that with sailors to find all the sailors who reserved red boats. And then we'll project it down to sailor name, and we get the names of the sailors who have reserved the red boats. Okay, we're just chaining this stuff along. Seem reasonable? Here's a more efficient solution. We're going to push some projections down. So we're going to take that boats table, and we're going to not only limit it to the red boats, but we're going to then throw everything about the boats away except for the boat ID, because that's the only thing we need to pick out the reservations for those boats. And then once we get the reservations for the boats computed, we're going to throw away everything but the sailor ID from those reservations, because I don't care what date it was or any of those things. I just need to know the sailor ID so I can join it with the sailor table. And then the result of that will project down to sname. So in some sense, we added some projections. Another way to look at this is we kind of pushed the projections down. At the end, we were going to throw away everything but sname. So what I did is I started throwing things away earlier. In fact, as early as possible. What's the benefit here? Let's assume projection is free or cheap, okay? And what is it saving us on? Join costs again. How does projection save us on join costs? There's the same number of rows going into the join after a projection as before. Yeah. Exactly. Although you have the same number of rows, they may be much skinnier rows after projection. You can pack more of them onto a disk buffer in memory, which means you do fewer IOs to your temp files when you're doing sorting or hashing or what have you, right? So you always want to squash those tuples down, even if you have the same number of tuples. Right? In fact, there's a whole sort of industry segment, a bunch of research papers in recent years, like what are called column-oriented databases. You may hear this when you go out in the field, or columnar databases. The big idea there, which is a pretty small idea, it's just kind of they beat it to death, was let's do projection as much as possible. Like, let's store the columns separately on the disk and only read the columns we care about. Let's have projection go before scan, essentially. So we've already stored the tables one column separately for the other. So when you do a scan of 3 columns, you just pick up those 3 columns from the disk. You don't read any of the other data, so it's less disk I/O. And then all the operations along the way are going to try to do things with as few columns as possible. All right? And when you only have things in single columns, you can even compress the columns. And so that's the whole trick of column-oriented databases, is basically push that projection down even into the storage layer. Question? I'm so glad you asked that question. So the question, for those of you who didn't hear, or maybe those on TV, was, are all these operations commutative? And the more general version of that question is, what are the rules for playing with these expressions? And that's why it's a relational algebra, actually. An algebra, right, a modern algebra is a syntax in which there are rules of things like associativity and commutativity of these operators. And it's the specification of those rules that defines what you can do in the algebra. So we're going to work on that answer to that question when we talk about query optimization. You're getting hints of it now. Clearly, we can do something about moving selection before join. Clearly, we can do something about pushing projection before join. But the actual rules for it I'm going to save for a little bit so we get a little more comfortable with the language, and we're starting to talk about query optimization. But those are exactly the right questions to ask. Commutativity and associativity are the basic things we're going to want to know about. And not everything commutes with everything. I'll give you a heads up. All right. Find sailors who have reserved a red or a green boat. OK. Well, we saw how to find sailors who reserved a red boat, right? Find the red boats. Find the reservations for the red boats. You find the sailors who reserve the red boats. Now I want red or green. Well, that should be pretty easy, right? I'm just going to change the selection to say red or green. You believe that works? I think it works. Let's see if it works. The slide's going to say it works, so it must be true. Okay, because if it's in the slides, it must be true. So we're going to, just for fun, throw in a row here. So we're going to take the boats table. We're going to do a selection where color equals red or color equals green, and we'll give it a name, temp boats. So now we've got this thing which isn't really a table at all. It's an expression called temp boats. In relational land, that's usually called a view. All right, a relation that's not stored is a view. It has a name. It's called temp boats. We can talk about it. It has a schema, but it's not a table. It's a view. All right. I think in Spark this is called an RDD. Right? It's a file of data that doesn't really exist, and we can generate it when you need it by having its expression and its lineage. Okay. So now that we have this view, we can use it in a query. We can say find the temp boats and join them with the reserves and the sailors and project down to S names. So those are the red or green boats, either boats that are red or boats that are green. Join them with reserves and sailors, get the S name, bingo. That's going to get us what we want. All right, that is correct. Now let me ask you another question. What about sailors who reserved a red boat and a green boat? Wouldn't it be nice if we could just take the previous slide and change the or into and? All right, so that would look like this. What's wrong with this query? Yeah. There are no boats that are both red and green, all right? There are lots of boats that are red or green. The red boats are red or green, and the green boats are red or green, right? But there are no boats that are red and green because it's a relational model, and you can only have one value in each color cell. Right? We're not allowing you to store multiple colors per cell. Okay, so there's no like, there's a red in there and a green in there. It's either one or the other, all right? And so this actually returns nothing. This returns the empty set. It's a well-specified query. It just happens to return nothing. All right, and so we're going to have to do something different. This is bad. What operation do we want to use? It looks a lot like the thing in the circle, but it's bigger. Intersection, right? So we're going to do a, sorry, cut you off. We're going to do a set intersection. Was that a question or an answer? There's an answer, yeah, good. So we're going to use intersect to do this. All right, so that's wrong. Let's make that painfully clear. So we're going to identify sailors who reserve red boats, sailors who reserve green boats, and find the intersection. Now, happily, SID is a key for sailors. There's only one row in sailors for each SID. So we can find SIDs from both of those two things and just intersect the SIDs. There's the red boats, temp red. There's the green boats, temp green. You take these two views and form their intersection and join it with sailors. And then you can project down to S name. Right? And in both cases, the only column we needed was SID from those two things, right? Cool. Questions? All right. That's it for today, actually. So the summary is the relational algebra is this little bitty language. It's a lot like the data flow systems that you are using, like Spark and MapReduce. It's a lot like the query plan iterators we described, but it's semantics. It's high-level language. It doesn't have an implementation. It just has a meaning. So, but it is operational, right? We nest these things in order. And that question that was asked by the gentleman behind the wall is exactly the kinds of questions you can ask about a formal language. What commutes? What associates? What rewriting rules can I use? That get kind of obfuscated when you're dealing with an implementation language. So you don't tend to ask those questions of implementations. It's nice to have the semantics written down. So it is operational. You nest things, but we know the semantics, and we can think about those nestings. It is a closed set of operators. So it's relations in and relations out, and you can mix and match and construct these sentences out of it. There's 5 basic operators and a couple natural compound operators, and set minus is the only thing that's non-monotonic. So I think that's everything you need to know about the relational algebra. You have a big homework due tonight. And I guess what you might want to do in the next 15 minutes is I can stick around, the TAs can stick around, and if folks want to use these 15 minutes to come ask us questions, please do. Good luck with the homework.